Yes. Okay. Hello, if we haven't met, my name's Mackenzie. I'm a PhD student at WashU working with Martha Prekup and Josh Reshian. And today I want to talk to you about two-row Springer fibers, so a very geometric way to think about combinatorial objects as well as their connections to the more algebraic side of Kazhdan Lusztig theory. So since it's a short talk, I'm hoping I'm going to state a main theorem that I've been talking about and interested in, and then work through an example that shows the result of the theorem. So I first want to start by stating a theorem. It was conjectured by Kazhdan and Lusztig and then proved by Francis Fung in 2002. And it says that co-dimension 1 intersections of irreducible components of a Springer fiber. And I'll explain everything after the theorem. Yield the edges of the Kazhdan Lusztig left cell W graph. Okay, so we're going to break this theorem down. We're first going to start looking at the Springer fiber side, so these codimension 1 intersections of irreducible components. And then we'll sort of backtrack and then look at it again through this Kazhdan Lusztig polynomial lens. So I'll work over here. So for this
2-row or just
2-row. Yeah, just 2-row. Or at least that's what I'll be talking about today. So let's denote our Springer fibers, or components of our Springer fibers, as curly B sigma, curly B tau, and sigma and tau are going to be standard Young tableau of shape LL. And we can index these Springer fibers with these 2-row tableau. And then a more concrete definition of a Springer fiber, right? If we have a nilpotent operator and we apply it to the complete flag variety, we want to see what is fixed by this operator. So it's the same as looking at this inclusion. And so in our example, I like to think about N as a matrix. So N has Jordan type, or block Jordan type LL coming from the length of the rows. So now let's look at an example. We have sigma as increasing along columns and tau as these tableau. So those are the tableau we'll be working with the rest of the talk. And what's really nice is there's a way that we can represent these tableau and these these components of Springer fibers as standard non-crossing matchings, and that allows us to then look at the intersections of those components. So I'm going to let C sigma and C tau be these standard non-crossing matchings. And how I'm going to define that is I'm going to have 6 points. And I'm going to take whatever's in the top row as a left endpoint of a cup and whatever's in the bottom row as the right endpoint of a cup. So just for simplicity, I'm not going to write 1 through 6 here, but if you believe me, the diagrams corresponding to these tableau are going to look like this. So it's interesting to look at these individually, but what we're really interested in, again, in the theorem, is the intersection of these components. So we can write that as B sigma C bar tau. So what I'm going to do is to represent the intersection, I'm going to pretend like I'm drawing a line through the points connecting 1 through 6. I'm going to reflect tau over that line. So what I'll end up getting in this case is this picture. And as we see, because we're working in this nice 2-row rectangular case, we're going to have a collection of circles. So up to homotopy, this is just going to be a collection of circles. There's a, oh, sorry. There's a theorem by Stroppel and Webster where they use these diagrams and count the number of circles to tell us how many fixed points or how many, what the dimension of the intersection of these two irreducible components is. So in our case, we're interested in codimension 1 intersections. So if we look at the codimension over the Springer fiber of B sigma intersect B tau, this codimension is going to be equal to 1 if and only if this cup diagram has L minus 1 circles. So in our case, right, we're connecting it back to the length of the row. So since L is 3 in this example, we want our diagram to have 2 circles. Here it does, therefore it intersects in codimension 1. So that's a very nice way to think about the intersections. And then another nice thing we can do is we can make a graph connecting. So having standard Young tableau as vertices, and then edges being, I drew it here, edges being, there we go, edges between standard Young tableau if they intersect in this codimension 1. And this is what the graph would look like for the L equals 3 case. Are there questions? Okay. So that's the Springer fiber side of it. Now, I want to connect this back to Kazhdan-Lusztig theory and why this theorem is actually very interesting. So we can also think about assigning a reading word to each of these standard Young tableau, right? So we'll say X sigma and X tau. So we're going to read bottom to top, left to right. Working with the same sigma and tau, we get X sigma as this, and X tau as that. And we need this because when we calculate the Kazhdan-Lusztig polynomials, which we've heard about today, we need permutations. We don't need standard Young tableau. So I quickly want to say we can re-index this. Think about to these standard tableau, have a reading word, and then we're calculating this mu bar value, which basically we want to calculate the coefficient of this power of q in our Kazhdan-Lusztig polynomial. So when this has a non-zero coefficient, this power of q in our polynomial, we add an edge between those vertices in the graph. Quick check for Bruja order, this is going to be equal q to the 0, and that is the constant term, which is equal to 1. Therefore, we have the coverings in Bruja recovered in our graph. And last thing I'll say is this yellow edge is the only non-Bruja edge in our graph. And yeah, that's because the polynomial is 1 plus q for X sigma, X tau, and that's why we have that edge. And they end up being the same graph, which is very interesting. Yeah. Thank you.
Do you have a question?
That's good. That means I was clear. Yes.
What happens when you intersect 3 or more components?
I'm not sure. That's what I want to look at. I want to look at different shapes of tableau and look more at these diagrams and see if just by looking at this, I can recover the power of q that I would like. But yeah, I haven't tried that yet. That's a good direction.
All right, let's say again.